Welcome to Year 2 differentiation. We're going to start by looking at what we can already differentiate, which is a reasonably substantial list. Basically any power of x. So this includes all polynomials, linear functions, quadratics, cubics, quartics, x to the power 12, anything that's got powers of x that are positive whole numbers, but also any power of x whatsoever. X to the 0, trivially included, we can differentiate a constant, it becomes 0. X to the half, in other words, the square root of x, we can deal with that. X to the power of a third, the cube root of x. X to the minus 1, x to the minus 2, x to the minus a half, x to the power of root 2, and all sorts of other weird and wonderful results. As long as you can write it as a power of x, you can differentiate it. We can also deal with various combinations of those. We can have 5 lots of x squared, or we can have x squared plus x to the 12, and we can still differentiate those. And we'll talk about how we combine different functions as well a little bit later. But there's a bit of a glaring hole in the functions that we can differentiate. If you look at your scientific calculator, you will see on there a pretty much complete list of what mathematicians call the elementary functions. These are the ones that appear all over the place in maths, and most things that you will deal with can be written in terms of these elementary functions. Also, crucially, any combination of them can be written as one, and the derivative of any of them is also an elementary function. So what kind of functions are we talking about? Well, here's a few important ones. Exponentials. There's an entire family of exponential functions, anything which can be written in the form some number to the power of x. This is a fundamentally different family of functions to x to the power of some number. Everything in the list at the top has some fixed number as the power. Everything in the list underneath, the exponentials, has a fixed number as the base and a variable in the power. These graphs are completely different to polynomials. The exponential curve is a fundamentally different creature, and so it's going to need some different approach when it comes to differentiation. And of course, if we've got exponentials, we shouldn't leave out logarithms, the inverse of an exponential. If we can differentiate exponentials, it would be nice if we could also differentiate their inverse function, logarithms. And again, because you can have any base for an exponential, we should be interested in any base for a log. Can we deal with log base 2? Can we do log base 1.2, etc., etc.? The other big gap that we currently have in our repertoire is the trig functions. Can we deal with sine and cos, the fundamental trig functions? And then from there, we will gradually build up to tan x, sec, cosec, cot. I would suggest, before we dive in and look at these results, in order for you to have a good starting point and to be more receptive to understanding where these results come from, why they're true, and in order to better remember them, it would be a good idea to try sketching these three curves first and have a go at also sketching their gradient function. You can spend as long or as little time on this as you like, and if you need to, you can use GeoGebra or some graphing app to draw the graphs for you, but see if you can sketch out what you think you know about the gradient function. Look at the steepness of the curves that you've drawn at each different x point. See if you can sketch out the shape of the gradient function, and then make a prediction about the kind of function that that might be. When you've done that, come back and we'll go through a few together. But first, let's look at a mass bouncing on a spring. I'm ignoring a few things here. We're going to treat this as if the only force acting is the restoring force of the spring. This particular spring stretches and then pulls when it's under tension, and it squashes and then pushes while it's under compression. We've got velocity and acceleration arrows. In order to understand what's going on with this kind of motion, you might find it helpful to try doing a sketch over time. Choose a suitable point for your 0 time, like the moment when the object is at its lowest point, perhaps just about to come up, and see if you can do a sketch of the displacement over time, then the velocity over time, and then the acceleration over time. See if you notice anything about the shape of your graphs. If you've done that, come back and we'll continue. We'll look at some trigonometry graphs. So here is our old friend, the sine wave, y equals sine x, and there's a few key points marked on there. I've marked on the key points because they will be the most useful to look at when we're trying to make a guess or a decent prediction about the kind of function the derivative of sine x would be. So if you look here, I've drawn on some tangent lines. At x equals 0, at x equals pi by 2, pi, 3 pi by 2, 2 pi, and then a couple more to the left as well. At each point, I've drawn the tangent lines, and hopefully you can see that those tangent lines look remarkably predictable in their gradient. The very first one, through the point 0, 0, looks like it has gradient 1. It appears to cross through the point 1, 1, and so on. So we go from a gradient of 1 to a gradient of 0 to a gradient of minus 1 to a gradient of 0 to a gradient of 1 again. Looks to me like the kind of function we've met before. In fact, because this function is periodic and will continue to repeat over and over again, whatever the gradient function is for this, that must also repeat every 360 degrees. Because if the graph is the same every 360 degrees, the gradient certainly is the same every 360 degrees. If we think about the oscillation we're noticing, the gradient going from 1 to 0 to minus 1 to 0 back to 1 again, it looks a lot like a cos graph. So this is going to be our working hypothesis for the time being. We think that y equals sine x should differentiate to give us dy by dx equals cos x. And that would be delightful. It's not the sort of thing that would work in degrees, but it looks like it would work like a dream if we're in the natural units for trigonometry, which is radians. Now let's look in a bit more detail at the official calculus approach. We take our function and we see what happens as we shrink a chord closer and closer until the two endpoints of the chord are essentially the same point. That's the essence of calculus. We take a chord and we look at what happens as the two endpoints of the chord get closer. Whatever the gradient of the chord is approaching as the length of the chord shrinks to nothing, that value that it approaches is defined as the derivative, the gradient of the curve at that particular point. Let's try it with sine x. You've done this before with x squared, possibly x cubed, where you needed a little bit of binomial theorem. But now we'll try with sine x and see where we get stuck. So f of x plus h is sine x plus h. And at this point, you might be thinking, last time we potentially looked at this, we didn't know what to do. But now we come back to it, having dealt with sine of a plus and minus b, we realize we have actually got a toolkit that might allow us to break this apart a little bit and look in a bit more detail at what's going on behind the scenes. So let's set it up. This is the way I usually do proof of a derivative from first principles. I don't worry about the limiting notation until the very end. I'm going to set up the gradient of the chord, m equals something, and there's nothing hazy or uncertain about whatever h is doing. H right now is not infinitesimally small, it's just a fairly small number. It could be 0.1 if we like. And this doesn't represent anything mystical, it's just the gradient of a straight line stretching from one point on the sine wave to another different point slightly further along. Later we'll worry about what to do as h shrinks to 0. But for now, we substitute our values in, and we make use of that sine a plus b formula from the formula book. Sine x cos h plus cos x sine h. And then the next bit may seem like it just jumps out of thin air, but there's a reason for this. The pieces within that penultimate line that stand out to me are the bits that have sine x or cos x in them. They're the pieces that won't change when h shrinks to 0. That means the rest of it is what I need to worry about. So I've tried to group it. I've taken out sine x as a common factor, and I've got the minus 1 from the end term, and I've got the cos h from the first term, and then all of that is being divided by h because of the bottom of the entire fraction. Taking cos x out as a common factor of this part as well with the sine h, and that's also divided by h. So now let's ask the question, what happens to those two bits? Is there any way to figure out what happens as h gets smaller and smaller to something like sine h divided by h, or cos h take away 1 divided by h? And it's not a bad idea at this point to try some small numbers, or even to look at the graph of sine or cos and think about what's going on very close to the origin. But if we're thinking about what happens to sine and cos for very, very small angles, then hopefully some bit of your brain, maybe the bit that still has the formula book open from the sine a plus b formula earlier, maybe you recognize that we've got small angle identities for exactly this purpose. If we're dealing with sine and cos of a small angle, then we know that sine theta is roughly the same as theta, and cos theta is roughly the same as 1 minus theta squared over 2. Now, for those of you who want to be even more rigorous, it might interest you to know that these are just the very beginning of what's called the Taylor series, which is essentially a binomial for pretty much any function that you know. We can construct this sort of thing using calculus, usually is how it's done, but this allows us to think of sine theta as a glorified polynomial. It's not really a polynomial, not in the usual sense, but it does have positive whole number powers of theta. The only issue is, slight snag, it goes on forever. However, if theta is going to shrink to 0, then the closer it gets to 0, the tinier these terms become. Theta cubed, theta to the 5, theta to the 7, they get really, really small. Which is why it's usually safe to ignore all the terms beyond the first one for sine theta. We've got everything up to and including any theta squared terms for both. There aren't any theta squared terms for sine theta, so we only end up with one term there. Now if we make use of those, we can see that cos h, because it gets closer and closer to being 1 minus h squared over 2, as h gets closer and closer to 0, our approximation gets better and better. And that means that we can replace cos h with 1 minus h squared. When you take away the 1 and you divide by h, we get minus h over 2. And the minus and the over 2 don't matter too much because as h shrinks closer and closer to 0, this shrinks closer and closer to 0 as well. In other words, that entire purple bit over here is going to become nothing. And similar reasoning can help us out with the green part, sine h over h. Well, if sine h is roughly the same as h, then we're just doing h over h, which is 1. And that bracket is 1. And there we have it, basically. Now we can see, since we know what happens as h tends to 0, we can say what happens to m as h tends to 0. We'll get sine x times nothing, add cos x times 1. That's what we're getting closer and closer to as h gets closer and closer to 0. Cos x. M tends to cos x as h tends to 0, therefore f dashed of x, the derivative of sine x, is cos x. That's what we suspected, is what we hypothesized by looking at the graph, and it turns out we can rigorously prove it. All we need is the assumption of this limit. This is the slightly hand-wavy bit of the proof, but this is the part that you'll be provided with in the exam. They'll say, you may assume that cos h minus 1 over h tends to 0, and that sine h over h tends to 1. So they essentially tell you these two pieces, and it'll be your job to make this leap here, to write it in an appropriate form so you can see how to use those limits in the right places. So here's our sine wave and cos wave, and a minus sine wave and a minus cos wave. What we're looking at is how to differentiate not just sine but cos as well. Because of course cos is just sine shifted sideways by 90 degrees. So if we want to differentiate cos, all we need to do is shift it sideways 90 degrees in the same direction. The difference is we don't end up at exactly the same place. We're still going 90 degrees along, so now we're 180 degrees away from sine. And if you move 180 degrees away from sine x, you get minus sine x. Now you could carry on. You could say from minus sine x, what happens if we differentiate? Well, we'll end up with minus cos x. And that's also a consequence of the fact that if sine x differentiates to cos, then anything multiplied by sine x will differentiate to that thing multiplied by sine x. Here's a nice way to think about it. We have a cycle. As we move 90 degrees, 90 degrees, 90 degrees, 90 degrees, we'll eventually get back where we started. So sine differentiates to cos, which differentiates to minus sine, which differentiates to minus cos, which differentiates back to sine again. Eventually, all those 90 degree shifts to the left will end up giving you a complete 360 degree shift to the left, and you're back where you started. Let's try an example. Y equals 3 sine x plus 4 cos x. We're being asked to find the first and second derivatives. So let's use the fact that sine differentiates to cos, and cos differentiates to negative sine x. 3 sine x becomes 3 cos x, 4 cos x becomes minus 4 sine x. We can go again. The cos becomes minus sine, the sine becomes cos. And now what we're looking at, if you look closely, if you compare these two things, look at y and look at the second derivative, d2y by dx2, and you'll notice that the second derivative is exactly the negative of the original function y. It's not a coincidence, that's what happens with anything that involves multiples of sine and cos exclusively. Sine with two 90 degree shifts will end up at minus sine, and cos with two 90 degree shifts will end up with minus cos. We could carry on as well. If you wanted to, we could look at the third derivative, and we'd notice that that one is the negative of the first derivative. And if we go one more time, well, we're right back to the negative of the original function. The fourth derivative is the negative of the second derivative, which itself is the negative of the original y. Therefore, the fourth derivative is the same as the original function. And this is exactly what happened on the previous slide. Sine becoming cos, becoming minus sine, becoming minus cos, and finally becoming sine again. One interesting thing that you may not have spotted here, 3 sine x and 4 cos x looks a lot like something we've dealt with in the trig chapter. It's possible to demonstrate that this can be written in terms of a single trig function, 5 times cos of x minus 0.644. And there's another way to write it as well. We're not required to write it as cos of x minus something. It's also pretty simple to show that it's the same as 5 times sine of x plus something. Those numbers, incidentally, are a difference of 90 degrees apart, which makes sense because the cosine is the complementary function to sine, so the functions are 90 degrees apart. You can either take a cos graph and shift it to the right by 0.644, or you can start with a sine graph and shift it to the left by 0.927. Either way, you'll end up with this function. This is the first derivative. And if you look closely, we can do a similar sort of thing to what we did in the previous one, but we'll end up with 5 cos x plus 0.927. So that seems a bit different, unless you compare it directly to the one above. Sine differentiates to cos. We will look more closely at what happens when you've got something other than x inside the function, but it certainly looks like, for now, nothing special happens. Whatever's inside stays the same. What happens inside a sine function stays inside a sine function. It's not always true, I'll be honest. There's always going to be some effect, but in this case, there's only one x in there, so the impact of shifting sideways is just to shift the derivative sideways. It doesn't affect the size of the derivative directly. When we get to chain rule, we'll talk about what happens when you try differentiating sine of 2x. But for now, It's just worth noticing there's a few patterns in here. No matter how you write out your trig identities or rearrange your trig expressions, when you differentiate, you'll find you get the thing that you would expect. You can even compare this second version to this original version here, and notice that the cos has turned into minus sine. So this one is in the same position in terms of the x minus 0.644, but cos differentiates to minus sine. In case you're curious, this is what the graph looks like. This is the first derivative, the second derivative, the third derivative, and then the fourth derivative is the same as the original, like we've seen before. So that shift of 90 degrees every time you differentiate is what links the sine and cos and minus cos trig functions together.